What if our intelligence doesn't come from a single place in the brain, but from thousands of tiny individual computers, each holding its own model of the world? These mini brains, also known as cortical columns, constantly learn and predict using sensory input, and together they help us understand everything around us. This radical theory of intelligence, the thousand brains theory, was the focus of our last video. In today's video, we'll dive deeper into this idea through three parts. First, what makes the thousand brains theory so different from conventional views of intelligence? Second, how do cortical columns do what they do? How do they learn, model, and map the world? And third, what does this tell us about artificial intelligence? Are we even close to building machines that think like us? Let's go. Let's try to understand why this theory is so different and revolutionary from conventional existing ideas of how the brain works. So according to the existing ideas, the way that neurons function in the brain is very hierarchical. You have an input, stuff is processed, you have the output. But stuff is processed kind of like in this hierarchy from A to B to C to D and so on. What this theory suggests is that information processing rather is instead distributed across a whole host of neural clumps called cortical columns within the neocortex. Now let's better appreciate this by considering this bottle of juice right here. So I know, for instance, that this is a pomegranate juice, therefore it should be red. I know that it has a list of ingredients. I know, without even giving it a second's thought, what it's supposed to feel like. The plastic feels cool against my fingers and so on. What I just described is my perception of what such an object should look like based on how my brain processes this information. And all of ours, actually, we're all in this together. But then the question becomes, if I have a bottle like this, and if information about any object, any arbitrary object, is indeed processed across thousands of different columns and is indeed distributed, rather than hierarchical. The question is, how do we still have a cohesive view of reality? How is everything that we see and perceive still intact? How are things not disjointed and completely disoriented because of all the different places that this information is being processed in? Where is it combined all together? The answer is actually, it's not combined all together, but really, as per this theory, these different columns vote. You heard that right. So it seems like there is a very democratic process involved, which can easily be explained with, for instance, this example of an optical illusion. At any given point in time, when we visualize something like this, we see either a vase or a face. This is because there are cortical columns in your neocortex. When you saw that image, they fired off, and then they decided to come up with a version of reality that best matches the image that they were seeing. It is not possible for us to hold both of these realities in our view at the same time. So when we see a vase, this is all that we see, and vice versa. Again, because of the voting scheme. Another very cool aspect of this theory is that everything that we perceive, each of our senses, sight, smell, touch, hearing, everything, and also the way that we recognize objects around us, the way that we make predictions, all of our higher order analytical thinking, everything that we do involves reference frames. Reference frame is basically grid-like structure. So when I say grid, you can think of it as this, a checker box like pattern. And according to this theory, everything that the brain processes is mapped using this reference frame scheme. In fact, the author even goes on to extrapolate this point into what it means for someone to become an expert in a field. So let's take the example of a concept in physics, say relativity. Now, when you and I think of relativity, we might think of Albert Einstein, or we might have some very disjointed ideas of what the theory means. That is arranged based on our reference frames. And we know relativity is somehow related to physics. It has something to do with light and so on. Versus if we have an expert in the field, and what better of an expert on relativity, let's say general relativity, than Albert Einstein himself. The author argues that where Einstein is different is that his brain also mapped the same concept using reference frames, the same way as ours does, except that he, as an expert and as the beacon of intelligence, has different reference frames. That's it. So even for something like the concept of general relativity, Einstein had reference frames because he started off with the same facts as all of his contemporaries. He started off with the same amount of initial information that was available to everyone in that day and age. But Einstein was able to arrange his information more systematically than most. To do that, he also used everyday objects. He thought of trains and people and flashlights and so on. So really, being an expert is about finding the best reference frame using which we can arrange facts and observations. Voting and reference frames, these are the key characteristic traits of our neocortex. And congratulations, this is what makes us human. So, what are the implications on AI? AI systems are not considered intelligent. They can only do one thing, whereas humans can do many things. Most AI systems today do not learn continuously. They are not flexible. The long-term goal of AI research is to create machines that exhibit human-like intelligence, machines that can rapidly learn new tasks, see analogies between different tasks, and flexibly solve new problems. This goal is called artificial general intelligence, or AGI. AGI would function as our brain functions. In order for that to happen, we need to know how our own brain functions. So in achieving these high-level AI goals, the author points to two prominent challenges. Number one, I do know that deep learning does not put us on the path to creating truly intelligent machines. We can't get to artificial general intelligence by doing more of what we are currently doing. To build truly intelligent machines, we must design them to adhere to the principles I laid out in the first part of the book. Intelligence requires reference frames. Needless to say, currently the way we go about implementing artificial intelligence does not account for any sort of reference frames. And the second major roadblock. Intelligent machines also need sensors and the ability to move them. This is referred to as embodiment. The embodiment could be a robot that looks like a human, a dog, or a snake. Most of today's deep learning networks don't have embodiment. Without embodiment, what can be learned is limited. So to answer the question asked in the beginning of the video, are we even close to building machines that think like us? We're working on it, but we're definitely not there yet. And we have a long way to go. Such a fascinating theory, such a wild theory. I had to stop multiple times when I read this book to process and reprocess what I was reading. So it was also a really good mental exercise. And I hope this video was as well for you. It gave you some food for thought. It gave you something to chew on. I will say one final thing before I go, and this is to quote the author. I don't want to leave you with an incorrect impression that we understand everything the neocortex does. We are far from it. And I think this is a very humbling realization and understanding, is that we don't know much about our brain, but it is still interesting and quite, I would say, rightly amusing to explore different theories around the same. And I did just that with today's video. Thank you, and until next time.